So we are back at AP Review. This is 2017 BC FR6. We are given that f of 0 is 0 and f prime of 0 is 1. We're then given an explicit formula to find the n plus 1th derivative at 0. It is negative n times the nth derivative evaluated at 0 for all n values greater than or equal to 1. Cool. A function f has a derivative of all orders for x values between -1 and 1 exclusively. The derivatives of f satisfy the conditions listed above, which I just went through with you. And the Maclaurin series for f converges for all to f of x for the window the absolute value of x is less than 1. Part A, show that the first 4 non-zero terms of the Maclaurin series for f are x minus x squared over 2 plus x cubed over 3 minus x to the fourth over 4, and write the general term. Cool. So the thing is, they already told me the answer. Now I just have to back it up, right? So I know that the way that this Maclaurin series should work, right? So I know what it should look like is f of 0, right, plus f prime of 0, technically over 1 factorial, but we never bothered to write it, x to the first, plus f double prime of 0 over 2, x to the second, right, plus f triple prime of 0, this is a 2 factorial, but over 3 factorial, x to the third, right? 2 factorial is conveniently just 2, right? Plus f, they wanted the first 4, so I don't need the fourth one. So dot, right? Plus dot, the nth derivative at 0, x to the n over n factorial. Great, cool. So dot, right? So now my job is to use what they gave me about f of 0 and f prime of 0 and so on. I am going to need one more. Hang on. I'm going to need the fourth derivative of f, and we'll talk about y in a sec. Sorry, had an aha moment. Okay, so I'm going to need that one, and we'll talk about y in a sec. Okay, so when I go to plug this stuff in, I say, oh, f of 0 is 0. Well, that was what I was about to do when I had that oh crap moment and was like, oh, that goes 0. So oops, they said the first 4 non-zero terms, which suddenly pushed me into needing another term. F prime of 0 is 1, so this is a 1 times an x. Now, that's what I was given. I'm now going to have to do a little bit of legwork to find some other derivatives, right? Because I specifically need the second derivative, the third derivative, and the fourth derivative, right? So I need the second derivative. In order to get the second derivative, if I think I've got a little room up here, right? If I want the second derivative, that's going to mean n is 1, right? That'll make f with a 2 up here, right? Second derivative at 0 should make n 1, so that's a -1 times the first derivative evaluated at 0, which is a 1. So, oh, look, that's a -1. So I get that this is a -1 x squared over 2. Great. Then I need to find f triple prime of 0, right? Well, f triple prime of 0 is going to be a -n, right? -n. And notice again, I used n as 1 to find the second derivative because this is f to the n plus 1 derivative, or the n plus 1 derivative of f. So I'm going to use n as 2. So when I plug in n as 2 to find the third derivative, and my third derivative is a little wonky there, but to find my third derivative, I'm going to get -2 times whatever the last one was, which was a -1. So, oh, that's a 2, right? So now I'm going to get that this is a 2 x cubed over 3 factorial, which we'll deal with, right? When I want the next derivative, which I'm running a little bit out of room for, but that's fine. So I'm going to plug n as 3 in and get that the fourth derivative at 0 should be -3 times whatever the last derivative was, which was a 2, so I get a -6. So I get -6 over a 4 factorial x to the fourth plus dot. Okay, so now we know that the nth derivative, right? We know the n plus 1th derivative, right? The nth plus 1 derivative is this thing, right? But we don't want the nth plus 1 derivative. We want this derivative, right? So we're probably going to need to find a pattern for this. We're probably going to need to find a pattern for this based on what we're seeing with the other stuff. So before we worry about the nth term, let's see what patterns we can find, right? So what I want you to notice is that what ends up happening is that I end up with this 3 times 2 times 1 canceling, right? And instead of using this guy as the pattern to figure this out, I'm going to be able to figure this pattern out by just looking at the pattern of terms. So they cancel and I just get a 3 on the bottom. Well, 3 was my n, right? And if you look at this is a 4 times 3 times 2. Oh, look, the 6 cancels with the 3 times 2 times 1, and I just get a 4, which is my n, right? So it looks like my nth term, I have a series that's alternating, right? And my nth term is just x to the n over whatever number n is, right? So when I plug in n is 1, I want to get a positive. So my nth term must be a negative 1 to the n plus 1, because if I just plugged in negative 1 to the n, then I'd get a negative 1 to the negative 1 to the first, which would come out negative, and I don't want that. So I get a negative 1 to the n plus 1, x to the n over n, right? So this was really useful for finding these, but it's not helping you to find this nth term, right? The way you want to find this nth term is by visual inspection from the other terms. So when all is said and done, I get exactly what they told me to show it looks like, right? It looks like an x minus an x squared over 2 plus an x cubed over 3 minus an x to the fourth over 4 plus dot 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 negative 1 to the n plus 1 x to the n over n dot 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 dot. And I double checked that I did everything they asked. They said show that this is the first 4 terms. I definitely did that. I did the work to show it. And then write the nth term, which I did. Cool. All right. Yes, and you can see all of that stuff. Cool. Part B. Determine whether the Maclaurin series described in A converges absolutely, converges conditionally, or diverges at 1. Okay, so I'm going to need this term. This is what's going to matter. So let's erase all this stuff and keep that term. Cool. So for part B, right, so for part B, at x equals 1, the question is, this term, right, the a sub nth term, would be a negative 1 to the n plus 1 x to the n over n, right? So the question is, at 1, does this thing converge absolutely, converge conditionally, or diverge, right? So here's the difference. Short answer is that if something converges only because some of the terms are negative, then it converges conditionally. Converging absolutely means that if you made every single term of this thing positive, it would still converge. So the most obvious example of this being a problem is when we end up with the harmonic series, which is exactly what's going to happen here, right? If I plug in x as 1, then my a sub nth term is going to end up being a negative 1 to the n plus 1. 1 to the n just goes away and doesn't matter. This ends up being the alternating harmonic series. Right? This is the term for the alternating harmonic series. Well, I know that the alternating harmonic series converges, right? But I know that the regular harmonic series, right, which is what would happen if I absolute value this, right, which is the absolute value of this a sub n that I have, diverges because the regular harmonic series diverges. So what we would say is that this thing converges conditionally. Right? It converges conditionally, not absolutely, because if you were to make all the terms positive, and in my brain I always think absolutely, like absolute value, if you were to make all the terms positive, this thing would not converge, because it would be the regular old harmonic series, so this thing converges conditionally. Let's see. Part C. Sorry, lost focus for a sec. Part C. Write the first 4 non-zero terms and the general term of the Maclaurin series for g of x equals the integral from 0 to x of f of t dt. And yeah, that's what they want me to do. Okay, so let's, again, the downside to using this board as opposed to using a piece of paper is that once I erase things, well, I'm in a situation where I've erased things. So for part C, right, we want g of x to be the integral from 0 to x of f of t dt, right? But we have already a series for f, right? So what that's saying is that we're integrating from 0 to x of, and then my f series, if it were t's instead of x's, was a t minus t squared over 2 plus t squared over t cubed over 3 minus t to the fourth over 4. And they only asked me for the first couple terms, but we'll keep going. So negative 1 to the n plus 1 t to the n over n plus dot, 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 right? That whole thing with respect to t, right? So that's what I want to find for g of x. When I integrate this, right? When I integrate this, oh, they said first 4 and the general term. There you go, 1, 2, 3, 4, and general. When I integrate this, I'm going to get t squared over 2, right? Minus, when I up this power by 1, right, I'm going to get t to the third over, well, now it's going to be a 3 times a 2, right? And then I'm going to have this plus, this will be a t to the fourth over, well, this is now a 4 times a 3, right? Minus t to the fifth, and this is now a 5 times a 4, plus da da da. So when I integrate this, it's now a t plus to the n plus 1 over an n plus 1 times an n. Okay, and I'm evaluating that from 0 to x, right? When I plug in 0, all of the 0 terms are going to go away, right? Because like all of them are zeros. They all have t's. So I'm going to end up getting that g of x is just what happens when I plug in all these x's. So it's going to be x squared over 2 minus x cubed over 6 plus x to the 4th over 12 minus x to the 5th over 20 plus oh, sorry, that was a negative 1 to the n plus 1 up there. Negative 1 to the n plus 1 x to the n plus 1 over an n plus 1 times an n. And you can distribute that if you want, but I don't think there's a huge reason to do so. Let's double check that we did that. Write the first 4 non-zero terms, 1, 2, 3, 4, and the general term. Boom, did it. Cool. All right. Lastly, part D. Let p sub n of 1/2 represent the nth degree Taylor polynomial about g, for g, which is the one we found here, about x equals 0 evaluated at 1/2. Where g is the function defined in part C, right? Use the alternating series error bound test to show. So what they want us to show in part D is that p sub 4 of 1/2 minus g of 1/2 is less than, and they want us to show that it's less than 1 over 500, right? That's what they want us to show, right? So here's the thing. If you're using, so when we talk about this error bound, what we do is we use the next term, right? So p sub 4 uses up to the x to the 4th term, meaning it uses these guys. In order to find the error, what we want to do is we want to max out the next term on the window between the center, which in this case is 0, and the point I plugged in, which in this case is 1/2, right? So I want to max this out on the window from 0 to 1/2. So what's going to happen is what I'm maxing out is this guy, right? And I don't care about the negative because it's inside an absolute value. So if I want to max out the x to the 5th, I'm going to do that by doing a 1/2 to the 5th, because 0 to the 5th won't be the biggest number. So I'm going to end up getting that this is a 1/2 to the 5th over 20. And I'm going to clean that up, right? So if I clean that up a little bit, that's a 1 over 32 times 20, right? Which is a 1 over 640. Well, 1 over 640 is definitely smaller than 500, right? So that's really essentially what they want me to show. So, or is smaller than 1 over 500. So bigger denominator, smaller fraction. So what I've shown is that this thing is smaller than this, which is smaller than this. So by the logic of things being smaller than other things, if this thing is smaller than this thing, it's also smaller than this thing.